Now let's move on. Now we have introduced the angular speed, angular velocity, and centrifugal acceleration. Then let's take a look at some of the motion. So let's do one very classic one. So let's say, let's take a look at, now let's say for a horizontal road, and a car wants to turn. This is a car. Okay. Whatever 係 bus 咯，好。Now when it wants to turn, so and what are the forces acting on the bus? Now why we need to derive the acceleration for circular motion, because we need to use a Newton's second law, FUMA, to relate the forces together. So in this case, you know, just those you have learned in last year doesn't mean that you can forget. We still need to use those knowledge. So we have the car has a weight, and also the what's the upward force. Yeah, that's a normal version. If the bus turns, so you can see I have drawn a part of the circle. Then you need to know that there is an acceleration towards the center of circle. So right now, I've just only drawn two forces. Do you think that the bus can turn in this case, but only these two forces? No. Because you know the acceleration is towards the center of circle. That means the net force is also towards the center of circle. But right now, it seems there's no other forces towards the center of circle. But indeed, the force is the friction. If the bus turns, the friction will point towards the center of circle. Then you can just write down that the friction equal to mass times the acceleration. And the acceleration is either V squared of R or R omega squared. I don't give you the values to substitute. It's just so simple. Then how can I draw the free 2D? I mean, you need to understand by yourself. You have your brain, You left it at home, then how can I help you? This is a circle. How can I draw that? You know? How can I draw? If you just look at 1D and then it just be a straight line. Then how can I draw the forces? We are all clever kids, you are all clever kids. You know how what I mean, right? We have been together for 3 years, and you don't understand what I mean. Yeah, let's break up. Like let's take a look at another case. Right? Let's take a look at roller coaster. So at the highest point of the roller coaster, at the lowest point, have you ever tried the roller coaster? In Ocean Park? Ocean Park. The one that you feel that you're upside down. Come on. You try it. The largest one. Oh. I think you need there's an age limit for this one. Come on. I'm not sure. Oh. I think if you have tried the roller coaster, wherever you have tried, but I think you know that how it works. So you need to climb up a climb up to a very high position, and then it will fall by itself without any other push. And it will just go and then till the end, and then it will disappear and break, and then it just slow down. Right? In the middle part of the roller coaster, there's no belt, there's no other pushing force, no other driving force on it, most likely. So for a roller coaster, and so this moving in a vertical circle is a vertical circle. So let's say at the highest point and at the lowest point. So let's say at the highest point, the speed is v, and the speed is u. The radius of circle is r. So let's consider at the lowest point. So what are the forces acting on the roller coaster? It will be the weight of this roller coaster, is it? And also the normal version. Normal version. Normal version. Now we just ignore the friction here. The friction will just slow down the speed, but not. The friction is tangential direction. It's horizontal. We just in this case, we just want to take a look at the forces towards the center of circle. Now, at the lowest point, we need to write down the formula, net force here, ma. So N, which one is larger, N or mg? They equal or they not equal? If you say they are equal, then the net force will be 0. But you know, in a circle motion, the net force will not be 0 because the acceleration is not 0. And how can we know which one is larger? You know the acceleration point towards the center circle. So N should be larger than mg, such that the net force will point towards the center circle. Okay. So therefore, it should be N minus mg. Then that's equal to mu square over r. If I give you a speed, okay. If I give you a speed, then it should be nu square over r. The net force. This is. He asked what is N minus mg. N is normal motion. N minus mg is the net force. Now, why is mu square over r? Because it's ma ma. A is a velocity square over r ma. We have derived it before. That is a centrifugal acceleration. That's b square of r. Yeah. Okay. Now, how about at the highest point? So there is a weight acting on the car. Yeah. But the normal motion that can point upwards or pointing downwards. It depends. If you're talking about a string, are you talking about a string? So let's say you just imagine, okay? You are, hold on. Wait, to see. So that's a string. So let's say I use this iPhone now. Let's bring it, okay? Let's bring it vertically. Listen. I'm very kind to you. No. If you consider the string is tied with something at the end, because the string always provides a tension. At the highest point, then the force acting on the object by a string will be downwards. But it's not the case in the roller coaster. It should not be the case in the roller coaster. Do you think that if the speed at the highest point is 0, then the roller coaster will fall? I think I should show you how the track in a roller coaster looks like. Yeah. So actually at the highest point, the normal motion can be upwards or downwards. And it depends on the speed of the object. So two cases. So at low speed, or even at the 0 speed, then the mg should be upwards. Sorry, the normal motion is upwards. But net force should still point towards the center of circle. So that means mg should be larger than n. Because you need to point towards the center of circle. Then use mv square over r. At the high speed, then the n will point towards the center of circle also. Right. Okay. It depends on the speed of the object. Done. If they are in the same direction, the net force will be larger. The V can be larger. No? If you do a subtraction, the net force is smaller, the V will be smaller. Okay. What do you mean by below? No. This is a below at the bottom. This is at the top. This is top. Yeah, we're talking this is at the highest point of the. Then how can we determine whether the speed is low or high? Then we can take, let's say if you take, so if n is 0, then you get mg equal mv squared over r, or v is square root gr. If smaller than this speed, you may consider it's a low speed. If smaller than this speed, then it should be mg minus n. If larger than this speed, it should be mg plus n. This is the case in the middle, or the critical case. N is 0. There's no normalization at the highest point. If the speed is exactly this value at the highest point, you feel that it's weightlessness. You feel the weightlessness at the highest point. Your pipette will be detached from your chair, okay? That's what we mean, hello? Weightlessness. But let's say if at a high speed, at a high speed 咧，唔係喎，never mind 啦，係差唔多啦。Which arrow? So let's say if that low speed, that means the speed is less than root gr. For high speed, it means the speed is larger than root gr. 咩嘢 call 條 equal to root gr, the notion is 0。咪寫咗咯呢個。But the bob or the ball is moving on a horizontal circle. So let me demonstrate to you. So it's just like this one. Okay. This is a conical pendulum. And then we also want to relate the tension, the weight, of the object and also angle of the object. Now let me test your common sense to see if you have or not. Yeah. So if the object is moving in a circle, if you increase the speed of the object, how about the angle? How does the angle change? Greater. The angle will be greater, is it? Genius, yeah. So m is the mass of the bob. Then later on we are going to derive the formula to see why the larger the angle, the larger the speed. Then first of all, now this question is not common in exams because they usually mix this topic with the next topic, gravitation. And you may think about the system with only the sun and the earth. Now for a conical pendulum, let's take a look at the three-point diagram of the bulb. So indeed, there's only two forces acting on the bulb. So one is the tension by a string. Another is the weight of the bulb. There's only these two forces. Now, that angle is theta, so therefore this angle is also theta. Is it? Yes. mg is always vertical downwards 㗎啦。好，哎呀，都係咯，嗯。Now then, how can we do it? Now, where is the center of circle? Here 咯，係先。This is the center of circle 嘛。It's moving in this plane 啊嘛。It's moving on this plane 啦。Then the center of circle, because we know for circular motion, the acceleration must point towards the center of circle. So therefore, here is the direction of the acceleration. And also we know that the net force should always point towards the center of circle. Okay. In this case, we should decompose the tension into two components. You have not done it for a long time, I know. So this one is T cosine theta, and this one is T sine theta. Now T cosine theta and mg are not point towards center of circle. T sine theta points towards center of circle. So therefore, T sine theta is actually the net force acting on the bulb. So T sine theta is a net force, okay? And that's your MA. And the A, because it's a circular motion, A can be written as V squared of R or R omega squared. Now let me use M R omega squared here. Now, given you that the length of the string is L, so how about the radius? Is radius L? No. You need to be careful about it. The distance or the length given may not be the radius. We'll see it tomorrow also. So in this case, the radius should be L sine theta. L sine theta. Can you see it? Can you see this right angle triangle here? So it should be L sine theta for the radius of the circle. And then T cosine theta equals to mg. But because the net force points towards center of circle, then the perpendicular direction this direction, then T cosine theta is equal to mg. These two forces will balance each other, such that the net force point towards the semicircle. And now, it's quite intuitive that we know that the larger the speed, or the larger angular speed, the larger the angle. But it's not that simple to look at this result from these two equations. So what we can do, now let's eliminate the t from these two equations. So this is the second equation. This is the first equation. So let's do the second divided by the first one. But the larger the angle, the larger the angle. Do you see that? Okay, can you do this algebra? Mg over ml omega squared. The mass can cancel out when you do the division. Now we look from this formula. G and L are constant. L is the length of the string. It does not change, even if you change the angle. G is 9.x1 is always constant. So look at this formula. There's only two variables. One is theta, and the one is the angle speed omega. So the larger the angle, cosine theta will become smaller if angle theta is larger. That's one problem in math. So larger the angle theta, then cosine theta will become smaller. Then this fraction will become smaller. Because this fraction equal cosine theta. Cosine theta becomes smaller, then this fraction becomes smaller. So that means that omega will become larger. Okay. You need to divide by a larger number, you get a smaller fraction. This fraction becomes smaller. Angular speed, yeah. Also, it means that it's moving faster. And if the angle theta is larger, I think although it's quite common sense, but we can still derive it from physics. Now, in most of the question, we will just relate circular motion with the gravitation. Almost within this recent 10 years, there's only one long question that include the circular motion only without the gravitation. So we will just focus on circular motion with gravitation, not circular motion only. So I'll give you some examples here. I'll also let you to take a look at the question with only circular motion. So we continue tomorrow because I don't want to start a new topic, gravitation. And then later on, there's some past data for you tomorrow.